Today we'll be starting with a new unit, right? And we'll be starting with the gravitation. And in gravitation, we'll be starting with the Newton's law of gravitation, right? We know according to Newton's law of gravitation, right? Every body will be attracting any other body, right? With the attractive force, which depends upon the masses of the two bodies, right? And not only masses of the two bodies, but also the separation between the centers of the two bodies, right? Or we can say the distance between the two bodies, right? So law of gravitation says that force of attraction between the two masses is actually directly proportional to the product of the two masses and inversely proportional to the square of the distance between them, right? So there were actually many scientists, right, who were working on this concept of gravitation, right? There was a Kepler, there was another scientist we call as Tycho Brahe, right? And then all these experiments by Kepler and Tycho Brahe were formulated in the form of a theory by Newton, right? And he thus gave forward a Newton's law of gravitation, right? The Newton's law of gravitation says that let's suppose we have two masses m1 and m2, right? The mass m1 will exert an attractive force on m2, and m2 will exert an attractive force on m1, right? So both these masses will attract each other because of the force of gravitation, right? Force of gravitation between them. And the force of gravitation between the two masses will depend upon the product of the two masses, right? And also on the square of the distance between them, right? So Newton formulated this concept of gravitation in the form of Newton's law of gravitation, that is force between two bodies is actually directly proportional to the product of the two masses, that's m1 multiplied by m2, right? And he also said that the force is actually inversely proportional to the square of the distance, right? So this law was actually formulated upon many experimental observations, right? And then Newton gave this law, that's the Newton's law of gravitation, right? So combining first and second, if we combine first and second, what we'll get is that F will be directly proportional to m1 m2 upon r square, right? R square, where r is the distance between the two masses, right? m1 and m2. Now replacing this proportionality with a constant of proportionality, right? And the constant of proportionality here is g, right? So it will be g m1 m2 upon r square, right? So this is the force between two bodies, right? This is the force between two bodies according to the Newton's law of gravitation, right? According to the Newton's law of gravitation. So the force between two bodies is given by g m1 m2 upon r square, right? Where g is nothing, it's a universal gravitational constant, right? G is a universal gravitational constant. Why is it universal, right? Because its value is same anywhere in the universe, right? Universal gravitational constant. And its value has been calculated as 6.67 into 10 to the power minus 11 Newton meter square per kg square, right? So this is the value of what we call as universal gravitational constant, right? So the value of the universal gravitational constant was calculated by Cavendish, right? It was calculated by Cavendish, was a scientist. Through the experiment, it was calculated by Cavendish, right? The value of this universal gravitational constant, right? And the force between the two masses is given by the product of the two masses upon r square multiplied by this constant. We call it as gravitational constant or universal gravitational constant, right? Now, this is the first point, that magnitude of the force between two bodies is Gm and m2 upon r square, right? Now, the direction of the force is along the line joining the two bodies, right? Along the line joining the two bodies. Force is directed along the line joining the two bodies, right? Force is directed along the line joining the two bodies. So it means that this is the mass m1 and m2. then the force between these two masses will be along this line, right? Which will be joining the centers of the two bodies, right? This is the direction of force because of force on one because of two, and this will be the direction of force on what we call as two because of one, right? And it's attractive force, right? It's a attractive force in nature, right? Gravitation is an attractive force, right? Attractive force in nature, right? Gravitational force is not repulsive, it's attractive force in nature, right? And since gravitational force is directed along the line joining the two bodies, right? So we can say that gravitation is a central force, right? Gravitation is a central force. It is a central force, right? So apart from being the central force, gravitational force is also a conservative force, right? It's a conservative force, right? So another property of this gravitational force is it is conservative in nature, right? It is conservative in nature. It is conservative in nature. Conservative in nature means that the work done in the gravitational field only depends upon the initial and final points, right? Or we can say the work done is path independent, right? Work done is path independent. Work done is path independent in gravitational field. So in gravitational field, the work done is path independent, right? And work done in a closed path is always equal to zero, right? Work done in closed path is always zero. Since gravitational force is a conservative force, the work done in a closed path will always be zero, and the work done will only depend upon the initial point and the final point, right? It will not depend upon the path followed, right? It will not depend upon the path followed, right? So these are some of the properties of gravitational force, right? And one of the important properties that it's a central force because the force is directed along the line joining the two bodies, right? And it is attractive in nature, right? It's a central force, right? It's conservative in nature. It means the work done is path independent. It will depend only on the initial point and the final point, right? And the work done is in closed path is always zero, right? In closed path is always zero. And the third point and the fourth point is that gravitational force always forms an action reaction pair, right? Or we can say it follows Newton's second law, right? Newton's third law. It follows Newton's third law, right? It means that if force F1 2 is the force on mass M1 because of mass M2, then the same amount of force will be on M2 because of mass M1, that's F2 1, and it will be directed opposite in direction, right? So it follows Newton's third law, right? And one more important point is gravitation is the weakest force, right? It's the weakest fundamental force, right? It's the weakest of all fundamental forces. It's the weakest of all fundamental forces. Gravitational force is the weakest of all fundamental forces, and gravitation is a long range force, right? Gravitation is a long range force, right? Right? So its range is very long, right? Very huge range for the force of gravitation, right? Now let's suppose we have two bodies here. We have two bodies here, mass M1 and M2, right? There's a force of attraction, mutual attraction between these two bodies, right? And if we take these two bodies as a system, right? If we take these two bodies as system, then there is actually no external force, right? There is no external force, right? F external is equal to 0 on the system, right? Because if we take these two bodies as a system, let's suppose these two bodies are in a system, as a system in a vacuum, right? They will attract each other. M1 will move towards M2 and M2 will move towards M1, right? But both these bodies as a system will have no external force, or we can say the total momentum will be conserved here, right? So P will be conserved. P total, that's momentum will be conserved here, right? Conserved. It means that if momentum of F1 is P1 in this direction, the momentum of M2 will be P2 along this direction, right? The total momentum of the system will be always conserved, right? Means P1 plus P2 will be equal to 0, right? It will be equal to 0. Or we can say P1 will be equal to minus P2, right? Right? It will be equal to minus P2. So at any instant, the P1 will be equal to minus P2, right? Because the total, because the system has no external force, right? The only force is the mutual force of attraction between them, right? So the external force is equal to 0. So the total momentum of the system must be conserved, right? In case of mutual force of attraction between the two bodies, right? Let's try to apply the Newton's law of gravitation to some of the questions, right? You can see here on the screen two spherical balls of masses 10 kg each are placed 100 meter apart, right? Find the gravitational force of attraction between them. So the gravitational force of attraction between them will be given by Newton's law of gravitation, right? That's F is equal to G m1 m2 upon r square, right? The value of G is 6.67, right? Multiplied by 10 to the power minus 11, and it will be the m1, that's 10, m2 is 10 upon r square, that's 100 square, or we can write that as 10 to the power 4, right? 10 to the power 4, so it will be equal to 6.67, right? Into 10 to the power 2, it will be 10 to the power minus 9, right? Minus 9 into 10 to the power minus 4, right? Or it will be equal to 6.67 into 10 to the power minus 13 newtons, right? So this will be the amount of force between the masses of the two bodies which are separated 100 meter apart, each of 10 kg. So you can see that it's a very small force, right? It's a very small force. So it means that in order to observe the effect of the gravitation, the masses, the two bodies should have a large mass, right? Or we can say the two bodies should be very closer to each other to actually measure the effect of this gravitation. You can see here the force of gravitation between, or the force of attraction between the 10 kg masses is very small. It's of the order of 10 to the power minus 13, right? When they are 100 meters apart. So we cannot observe this effect between the smaller masses, right? But if one of the bodies is very huge, right? Like we have the Earth and any other body, right? So Earth has the huge mass, right? It means that the gravitational force because of the Earth will be significant, right? It will be significant, and it is significant, right? And that's why we are easily able to observe the effects of the gravitation on Earth because of Earth, not because of the smaller bodies, right? Because of this value of G, gravitational constant, it's of the order of 10 to the power minus 11, and because of that the force of gravitation is actually very small, that cannot be observed physically, right? Now let's discuss this question. Two particles of mass 1 kg and 2 kg are placed at a separation of 50 centimeter, right? Assuming that the only force acting on the particles are their mutual gravitation. Find the initial acceleration of heavier particle, right? So the initial acceleration of the heavier particle will be the force on the heavier particle, right? Upon the net mass, right? On the net mass. Let's suppose F is the force, and mass of heavier particle is m. So it will be F upon mass is 2, right? It will be 2 kg for the heavier particle. Now I have to calculate the value of F. F is nothing, it's given by G m1 m2 upon r square, and value of r is 0.50 centimeter or half meter. We can write it as 1 by 2 whole square, right? That will be equal to 6.67 into 10 to the power minus 11, right? Multiplied by 1, multiplied by 2, and multiplied by 4, right? So it will be 6.67 into 8 multiplied by 10 to the power minus 11, right? Now let's put the value of F in this equation. We'll get the acceleration of the heavier mass, that's 6.67 into 8 into 10 to the power minus 11, right? Upon the factor of 2, right? So it will be 24, right? 8 6 is 48, right? 48. It will be 50. 2.8, right? 52.8, right? Upon 2, or we can say that it will be equal to 24, 26.4, right? 26.4. 26.4 into 10 to the power minus 11 newtons, right? Or it will be equal to 2.64 into 10 to the power, not newtons, right? Newton, 2.64 into 10 to the power minus 10 kg meter per second square, right? Or we can say it's a value, it's the acceleration we are calculating, it will be meter per second square, right? It will be meter per second square. So 2.64 into 10 to the power minus 10 meter per second square will be the acceleration of heavier mass, that's 2 kg mass. Now talking about the force due to multiple charges, right? Let's suppose we calculate the force of gravitation between the two charges, right? When we had the two charges in place, right? Now, how will we calculate the force between the two particles, force on the particle because of the multiple particles, right? Because of the multiple particles. Now, let's suppose we have many particles, right? Mass m1 is there, right? And we have mass m2, right? We have mass m3, right? And we have mass m4, right? M4 here. Now there will be force of attraction because of each of these masses, right? Force of attraction because of each of these masses, right? Let's suppose this is F1, this is F2, right? This is F3, right? This is F3. Then the net force on this mass M1 will be given as, it will be the vector sum of each force. That's F1 vector, this F2 vector, right? This F3 vector. So this is what we call as the force between the multiple particles, or we call it as superposition principle, right? It is the superposition principle. It means the net force on each mass will be the vector sum of all the forces because of other particles, right? So that's how we can calculate the net force on a given mass, right? Here you can see that find the net force on 2 kg, 2 to 3 kg and 4 kg particles, right? It's like we have 2 kg here, right? We have 3 kg here, right? And we have 4 kg here, right? 4 kg. Let's suppose the separation between them is 2 meter, and this is also 2 meter, right? 2 meter. Now the masses, each of these masses are 2 kg, right? 3 kg and 4 kg, right? We have to find the net force on 2 kg due to 3 kg and 4 kg. So because of 2 kg, there will be attractive force, right? Because of 3 kg on 2 kg, and there will be another attractive force because of 4 kg on 2 kg. So the net attractive force will be equal to, since both the forces are along the same direction, so the net force will be addition of the two forces, right? So it will be equal to G m1 into m2, right? So it will be G m1 into m2, that's 2 into 3 upon 2 square, right? Plus G 2 into 4 upon, now the distance is 4, that will be 4 square, right? So it will be equal to 3G upon 2, right? Plus it will be 2G upon 4, or we can say it will be equal to G upon 2, right? Or that will be equal to 4G upon 2, right? That's equal to 2G, right? 2G. And the value of G is 6.67 into 10 to the power minus 11 Newton. So this much of force will be here between 2 kg mass and 4 kg mass, right? Now you can see here we have three particles placed at the corners of an equilateral triangle, right? M, M, and M each, right? We have to find the net force on one of the particles, right? On one of the particles. So let's suppose this is the particle where we have selected for the calculation of the net force, right? Now there will be two forces on this particle. One will be because of this mass, another will be because of this mass, right? And the total force on this particle will be the vector sum of both the forces, right? And we can see that the both forces are actually at an angle of 60 degree because it's an equilateral triangle, right? Equilateral triangle. So the net force will be, let's suppose F1 is equal to, F1 will be equal to G times M1, M2, that's Gm square upon A square, right? And F2 is also equal to Gm square upon A square, right? So the net force will be equal to under root of Gm square upon A square, right? Plus Gm square upon A square whole square, right? Multiplied by, right, plus 2ab cos theta. That will be twice uh, Gm square upon A square whole square, right? Cos of theta. Cos of theta is cos 60, right? That's 1 by 2, right? That's 1 by 2. Now we'll be left with 3 times, right? It will be A square, that's this, and B square, right? Now it will be equal to root 3 times, right? It will be root 3 times Gm square upon A square. That will be the net force on this particle, right? On one of the corners of an equilateral triangle. Now, similarly, I can see here we have 4 particles placed at the corners of a square, right? Now we have to calculate the net force on one of the particles on the square, right? Now there will be 3 forces, F1 because of this mass and F2 because of this mass, and the third force will be the mass along the diagonal, right? Let's suppose that is F3, right? Let's suppose that's F3. The value of F1 is equal to Gm square upon A square. F2 will be equal to Gm square upon A square once again, right? And the value of F3 here will be equal to, we know the distance, if this is A, then this distance will be root 2A, right? So the F3 will be equal to Gm square upon root 3A square, or we can say 3A square, right? 3A square. Now calculating the total forces, right? Now the resultant of F1 and F2 will be, resultant of F1 and F2 will be along this direction, right? Along this direction. And the resultant will be actually root 2 times this, right? So the resultant of, we can say that F1 vector plus F2 vector will be equal to root 2 times of this Gm square by A square, right? Right, and it will be along the direction of this F3 vector, right? So the net force here will be equal to, F net will be actually equal to, right? The net force in magnitude will be equal to root 2 Gm square upon A square, right? Plus Gm square upon 3A square. So this will be the net force on this mass M placed at the corner of square, right? At the corner of square. Now infinite particles, each of mass M are placed at positions x equal to 1 meter, x equal to 2 meter, right? X equal to 4 meter, right? And so on. Find the magnitude of the gravitational force on a particle at origin, right? So it means that we have, let's suppose this is at mass M at x equal to 0, right? Mass M at x equal to 0. Then we have mass M once again, right? At x equal to 1 meter, right? We have mass once again M at x equal to 2 meter, right? And then we have mass M x equal to 4 meter, right? And so on, right? Up to infinity. So this is infinite mass distribution, right? The distribution here is infinite. It means infinite number of particles is actually placed here on this line. We have to calculate the net force on this mass M placed at the origin. So the net force on this mass M placed at the origin will be the total force because of each of these masses, right? Because of this, because of the each of these masses, right? Total attractive force because of each of these masses, right? So this will be the attractive force. Now calculating the net attractive force, right? It will be equal to, because of this M equal to x equal to 0 and x equal to 1, the attractive force will be Gm square upon 1 square, right? and then we'll have gm square upon 2 square, right? Then we will have gm square upon 4 square, right? And so on, right? And so on. Now you can see here, it will be up to infinity, right? So the net force, you can see here, it actually forms a GP, right? Actually forms a GP. The net force will be actually equal to gm square, right? To 1 plus 1 by 2 square, right? Plus 1 by 4 square, right? And so on. It forms a GP, right? And then infinite sum of infinite GP is actually equal to A upon 1 minus R, right? Here A is the first term, right? Which is here equal to 1. And the common ratio, you can see here, the common ratio here will be, it will be 1 upon 4 upon 1, right? That's 1 upon 4, right? That's 1 minus 1 upon 4, right? That will be equal to 4 upon 3. 4 upon 3. So the net force here will be actually equal to, the net force on this particle here will be actually equal to 4 upon 3 or 4 gm square, right? It will be 4 gm square upon 3. So this will be the net force on the particle, right? Because of this infinite distribution, right? Now let's talk about let's try to calculate the force of gravitation because of the continuous mass distribution, right? Now we can find the force of gravitation because of the continuous mass distribution as well, right? You can see here, we have a particle of mass m is placed at a distance of d from one end of mass m, right? From one end of mass m, right? And length L as shown in figure. Find the gravitational force on the particle by the rod, right? Now let's suppose if we try to find the net force because of this rod on this particle of mass m, right? And we know that since it's not a point distribution, point mass distribution, it's a infinite continuous mass distribution, right? It's a continuous mass distribution. What we will do is that, let's suppose we'll take at a position of at a distance of x, right? At a distance of x, we'll take an element, right? Dx, right? Element dx of mass dm, right? Of mass dm. Now, because of this dm, the force of gravitation between this mass m and dm mass will be actually a small force df that will be equal to g times, right? M into dm upon the distance square, that will be equal to x square, right? So this will be the force, right? Now to calculate the net force on this mass m, we have to integrate it on both sides with the proper limits, right? Now talking about the value of dm, we know that mass per unit length will be actually equal to dm upon dx, right? Or we can write this dm equal to m by l into dx, right? M by l into dx. Now replacing the value of dm with m upon l into dx, right? We'll get integral of gm, so it will be m. Now integrating it on both sides, right, with the proper limits. So we'll have m by l here, gm into m upon l, right, multiplied by dx, and we have x square in the denominator, right? Now we have to integrate it with the proper limits. Now you can see here the continuous mass distribution is from distance d to distance d plus l, right? D to d plus l. It means that we'll have to take the limits from d to d plus l to calculate the net force on this particle of mass m, right? So it will be equal to integral of df, that will be f, right? Now integration of 1 by x square will be equal to minus 1 by x, right? It will be minus 1 by x with the limits d to d plus l, right? The limits d to d plus l, right? Now taking the upper limit and the lower limit, GMM upon L, we left with 1 by D, right? We left with 1 by D minus 1 by D plus L, right? 1 by D plus L. So this will be the net force on this particle of mass M, right? On this particle of mass M, on this particle of mass small m, because of this continuous mass distribution of rod, right? A small object of mass m rotates about a very large and heavy object, mass m with constant speed v naught, then find the radius of its circular path, r, right? So a small of object mass m rotates about a large object and a heavy object, right, of mass capital M with constant speed v naught, then find the radius of its circular path. It means that let's suppose we have this large mass m, right, and small mass m, right, and because of the force of gravitation, this mass m is actually revolving in a circular path, right? We have to find the radius of that circular path, right? Now we know that because of the force of gravitation, the necessary force for this particle to be in circular path will be a centripetal force, right? And that will be equal to the force of gravitation here, right? Now the centripetal force is mv square, right? That will be mv naught square upon r, right? That will be equal to the force of gravitation here. That's equal to gm m upon r square, right? Now this r and r will get cancelled, right? M and m will get cancelled. The value of V naught or value of R will come out to be equal to, that will be equal to V naught square, right? Or that will be equal to GM by V naught square, right? So this will be the value of R, right? Or this will be the radius of this circular path. Or the velocity will be equal to V naught. That will be under root of GM by R, right? That will be under root of GM by R. So this will be the speed and this will be the radius of this particle, right? Now talking about the law of gravitation in vector form, right? We can write it in vector form as well, right? We can see here we have two particles of mass m1 and m2 each, m1 and m2 each, right? Let's suppose uh, the position vector of m1 is r1 vector and position vector of m2 is r2 vector, right? So there will be a force of gravitation or force of attraction between m1 and m2, right? It will be along the line joining the two bodies, right? Now let's suppose this is the direction of force on 1 because of 2, right? Force on 1 because of 2, f1 2 vector, right? That will be equal to g m1 m2 upon, right? Let's suppose the distance between them is r, right? That will be r square, right? Now, if this is r1 vector, this is r2 vector, so this will be the displacement vector r vector, right? This r vector will be equal to r2 vector minus r1 vector, right? R2 vector minus r1 vector. So this will be the r vector, right? Now, if this is the r vector here, this is the direction of r vector, right? If this is the direction of the r vector, then the force on 1 because of 2 will be along the direction of unit vector of this r vector, or we can say it will be g m1 m2 upon r square, that will be multiplied with the unit vector r cap, right? Unit vector r cap, or we can write this unit vector r cap as, it will be uh, mod of r vector, right, upon mod r vector upon mod of r vector, right? Or we can write it as g m1 m2 upon r cube multiplied by this r vector, right? R vector. So it means that the net force in the vector form will be equal to g m1 m2, right? Now r cube is nothing, it's the magnitude of r2 vector minus r1 vector, right? Cube multiplied by this r vector, right? R vector, and this r vector is equal to r2 vector minus r1 vector, right? So the force F12 in the vector form will be g m1 m2 upon mod of r2 vector minus r1 vector cube, right? and multiplied by this r vector. That's r2 vector minus r1 vector, right? So this will be the force of gravitation or gravitational force in a vector form, right? This will be the gravitational force in a vector form. So we'll stop here. We'll be discussing gravitational intensity in the next lecture, right? That will be started. That will be discussed in the next lecture, right? So we'll meet tomorrow for the day after tomorrow for the next lecture. Till then, take care and goodbye.